Hi everyone, welcome to Ground Zero AI, and we are starting with week 4, and today is day 1 of NLP, and we are starting with three topics named topic modeling, dependency parsing, and co-reference resolution. So, starting with topic modeling, we'll see in detail. We'll be covering LDA and LSA techniques. So, let's start with let's build up some context of what topic modeling is actually and why is it needed. So let's start with when you scroll up Twitter feed, right? Like you see large number of posts with covering different domains, maybe tech or politics or some kind of news, right? So you naturally group those kind of stuff back of your mind, like what the basically context is. Uh, like also when you browse web or even organize your emails, like you send to recruiters or maybe some other collaborator of yours. So you naturally try to group those sent emails, right? So how can machine do this for us? And this will be the context we'll be talking about in this session. So more such examples also, like we can also talk about like news clustering as well, because there, if we read a general newspaper, there are pages maybe of politics, sports, or tech, or some other Hollywood or Bollywood news. So you try to. So it is already been segregated, right, about the it is talking about. But the main agenda is how the machine is doing this for us. So we'll be looking into it, and yeah, I think this is clear for you right now. And then like we can start with the next one. Also, as you know, we generate and consume a lot of data on day-to-day basis. There was a report where they talk about per day, like we are generating about data in quintillion bytes. So that is also a concern because the data could be structured or unstructured, and most of the data, like more than 60 or 70% of the data, is actually unstructured. So here, topic modeling also comes into the picture. How we are actually looking up onto that data. Let's start with an example. Let's say uh, we have three such just statement, or let's say this is the data, and we are talking about three different topics actually. Like first is new AI model being beats benchmarks, second one stock markets its all-time high, like, third is welcome to Grand AI. So these are three different topics, and the machine should be able to actually understand what the basic context is and how we are going to further scale or actually get information from this data, right? Also a question may arise why we are actually employing machines for these tasks. Because see, like if you're working in a company, or let's say it's a business and it employs just a single individual to review each piece of data that is majorly unstructured, and it tries to segment them based on the underlying topic. So it would be really not easy, it could be an impossible task for any such individual, because unstructured data could be of any sort of form. So it would take a good amount of time to actually complete, and also be an extremely tedious stuff. Plus there is a lot of risk involved, since human are bit naturally biased and more error prone than machines. Because if I am reading new AI models beat benchmarks, like this is one my such observation that yeah, it's happening, and could be a lot of uh, observation that I am seeing. So but for a different individual it could be a different perspective. So yeah, like every such topic is different for us human, like how we are actually perceiving that. But for machines, it could be a case that we want to actually get output from machine how it's actually perceiving it, right? So before diving into topics and what topic modeling techniques actually are, we'll be looking into bag of words, and let's start with an intuition what bag of words actually is. So here, if you see, we have three such. Let's say these are actually documents, and for each document, we try to uh, get unique words from here. So basic intuition is we simplify text in these documents into numbers, and a sentence becomes a vector of these word counts, because like for each every such sentence there is kind of unique word, right? And for that unique word, we try to get a count of that word in that particular sentence. Uh, like if we talk about steps, so the first step is basically what we call tokenization. So tokenization if put up in simple words, is basically breaking down sentences into words as simple as that. Next is vocabulary creation. Like we define a unique set of words across all text, uh, and we put up in the this bag of words matrix, which we are saying as document, AI, model, stock, market, ground zero. Like these are actually our words, and for we are actually building up this matrix for these three documents. So here, if you say like for like AI just comes in document one, and similarly model just comes in document one. Stock market comes in document two. So this is how we are actually building up bag of words matrix. I guess we are now pretty much clear with what BOW is. Next, also let's give a short description about TF idea of technique. And what TF idea is basically, we highlight important words for a document while downplaying frequent yet generic words. Could be like what we actually use as kind of helping verb. Let's say is kind of like one word could be is, or like or article, right? The, a, and kind of words. So yeah, like idea is basically we are highlighting important words for a document, and TF-IDF is basically term frequency and inverse document frequency. And this is actually important because let's say if you are actually here using new AI model beat benchmarks, so AI might be highly relevant in this one document but not in a corpus about finance. So this is one such example where TF-IDF comes into picture. And like for just hands-on, you can uh, convert this bow matrix, bag of word matrix, into TF-IDF matrix. Like for the references, like we'll be providing references for how to actually compute this stuff. Or also, if you haven't watched the lecture one yet, you like we'll just suggest just watch that. So I guess we are pretty much clear what we have talked about till now. Let's dive into what topic actually is, and then we can continue what topic modeling. So, what topic actually is? Basically, we define topic as a latent theme, or more generically, we can say it's a hidden theme that groups similar words and documents, right? So let's say we have an example. Let's say we are creating a topic. Let's say name one, and it could be like AI model, or let's say algorithm. So from very just basic intuition, we can say that AI model algorithm can be part of topic one, right? And if you are trying to build up another topic two, that can be, let's say, stocks, market, or let's say zero. So yeah, it could be said that AI model algorithm can be part of topic one, and stock market zerodha it can be part of topic two. So we try to group these words in just one topic, and yeah, it should be a question why we need topic models. So we need to first find what the problem actually is. Then we can move on to what topic model actually is. So problem is basically the way we are actually capturing bag of words matrices, or how TF-IDF actually captures. So it just only surface level information. What it actually is. It's just a uh, vector matrix, right? So the solution is basically we topic models reveal deeper semantic relationship, and that is why we are diving into this, and we'll be covering in a good detail how topic modeling is actually solving the semantic relationship problem. So let's start with topic modeling techniques, and here first we'll be talking about LDA. So LDA is basically let's start it here. LDA. It's basically latent Dirichlet allocation, and we'll be looking into what the basic intuitive idea about LDA is and how it's solving the basic semantic problem, or what's actually the process look like. So it's just a probabilistic topic modeling technique that assume that we have documents, whatever documents, like here we have three such documents, right? So these documents are mixture of topics. That makes sense. Next, topics are actually mixture of words. Yeah, that also makes sense. So let's try to make it more intuitive for you. So imagine you have a collection of documents, right? You have three such documents, and you are trying to discover hidden topics, right? So each document talk about a few topics, and each topic has its own distribution of words. So let's say example one, we have this document first, where 70% of this uh, document talks about technology, and let's say 30% about, maybe if it can be more elongated, let's say 30% about finance. And in document two, let's talk about 50% about uh, stock market, and rest 50% about health. So yeah, it's more like we are uh, giving what composition of area the words are actually having in that particular document. So these topics are probabilities for words. Like example, maybe this technology might heavily feature words like AI, algorithm, data. So this is how we are actually dividing this stuff. And the basic goal of LDA is to figure out a big distribution for each document. And next is we want to have word distribution for each topic. So yeah, this is the goal of LDA, and how we are actually going to process this stuff is the main goal. And so basically, first step will be we'll have an let's say change the color. So we'll have an input, and input is basically is a bag of word, like maybe document or word count. So the next step is pretty interesting. It's a generative process. So next is a generative process, where for each document we randomly assign a topic to every word, and we reassign topics iteratively based on how strongly the words fit in a topic and how strongly the topic fits the document, right? So let's give it strongly the words fit the topic and how strongly the topic fits the document, right? So yeah, like we are looking into this, and what we expect as output is first thing is document topic distribution, what topics are present in each document, and the next is topic word distribution. So what words define each topic? So the major focus is basically on two things: topic and document. I think it is clear till this point. Cool. Also, let's talk a little bit about mathematics behind LDA. So uh, the basic formulation can be mentioned as this equation actually. So here LDA uses the Dirichlet distributions, which are nothing just probability distribution. So here we define a Dirichlet prior, like that controls the sparsity of topics in documents and the words in topics, and it's just basic of Bayesian approach that infers topic distribution. So here we are actually talking about, let's say Z is the topic, T is the document, and W is the word. So here what we are actually formulating is basically Z is the topic, and for like it's just a condition probability word document for that particular topic. And next we'll define a just condition probability or PWYZ. This is basically this topic and for that particular word, and we are actually calculating this independent even probability. Next we have uh, also, let's talk a little bit about what advantages of LDA is actually. So, as we see, the formulation is probabilistic, right? So, it helps uncover the soft topics where document can belong to multiple topics, right? Yeah, it can work for large corpora as well. So, this is what basic LDA is. I think so far it has made sense to you. And yeah, let's move on to next one. Cool. Let's talk about LSA. LSA is basically latent semantic analysis. Let's mention it here. Okay. So here we are talking about LSA is basically a more like linear algebra based technique that uses matrix factorization to find topics in the text data. So if we talk about intuition, so here it can be said that the words that appear in the similar context are related, right? So we try to reduce the high dimensional document term matrix to lower dimensions that capture latent or we say hidden relationships. So basic example could be like we have original dimensions, right? Like words like AI or let's say algorithm or learning, right? So we reduce these dimensions, right? Like two dimension can be mentioned as just one topic. Let's say topic one, that is machine learning. right? So I think you have got the idea what actually LSA is. We are just reducing the three such dimensions, yeah, three, the higher dimensions to lower dimensions to, or reduce dimension, as we have converted AI algorithm learning to just one topic called machine learning, right? So what actually the process of LSA is? So again, we have input of, as we have mentioned, so actually bag of words or set clear idea of. Next step is we do a matrix factorization. So we decompose the document of matrix T into three matrices that can be mentioned as equal u dot summation of v transpose. I can. So this is basically the how mathematical formulation of decompositions look like. So here, what u is basically, I think just a dot product actually. Yeah. So U is document topic relationship, and we do a summation of importance of topics. This summation symbol, like this is actually talking about the what importance of that topic is, and V transpose is basically what topic or relationships, right? So this is just if we have just linear algebra, the basic essence of linear algebra, it's just a singular value decomposition, or like you may also revisit the concept. It is very simple thing. So next step is dimensionality reduction, where we retain only the top case singular values or topics, removing the noise. I just mentioned p2 dimension reduction, where we retain okay topics, right? So regarding mathematics, so the SVD process approximate D uh, while preserving essential structure, and the topics are actually essentially directions in the reduced vector space, as we are coming from high dimension. So what advantages can LSA possess is it is uh, as you see it is basic dot product of these three terms, right? So it is very simple and fast, and it captures hidden relationship between words and document using this geometry. And yeah, as it is coming from high dimension to low dimension, it is actually useful for us to summarize the topic what it's actually talking about. And if you want to compare what LD and LSA differently are, so we can talk about basically approach. Yeah, so let's say LDA. LSA. So for LDA, the approach is bit probabilistic, and for LSA, it's linear, just a simple linear algebraic equation. It's SVD, right? And for LDA, the output is the probability of topics and words. For LSA, it is latent vector space for document or words. Like, and in terms of flexibility, like we can say that for LDA, the model can model soft clusters, like document has multiple topics, and for LSA, like it tends to create harder clusters, right? So this is just basic difference, and major question could be when to use LDA or when to use LSA. So for LDA, we can say that when you want interpretable and probabilistic topic distributions, right? Like that is great for large data set with distinct topic where we want to have like probabilistic approach. And for LSA, when computational simplicity is needed, or like as a quick exploratory step that could give a better idea for us to uh, summarize a lot of documents, right? So yeah, this is all about LDA and LSA. We can move forward to next topic now. Yep. Good. Let's talk about dependency parsing now. To just mention. So the basic idea behind dependency parsing is it's a syntactic analysis method used in NLP to understand the grammatical structure of a sentence by identifying the relationship between words. So it focuses on dependencies, or let's say you can say it's a link between words where one word governs, or you say or depends. Honestly, the major focus of a dependency passing is like this depend what actually uh, between two words or another word, right? So why dependency passing is basically let me formulate this way in this way. Let's say uh, it asks two questions. Basically, it answers questions of two right. Just a second. Basically, what happens is in dependency parsing, it answers who does what to whom, right? And the next question is which words are related and how. So these are two questions which we try to answer from dependency parsing, and it has many applications, right? So first could be like information extraction, where we extract subject, object, or predicate. So what the constituent of a particular sentence is, let's say welcome to ground zero AI, right? So here the subject is basically ground zero, right? And we are also framing timing, right? Like we are actually framing the word when. So each word actually constituted is the constituent of different uh, parts of speech. So also next application could be question answering, where we resolve relationship in questions. Could be a semantic role labeling, where we identify roles like what is the agent, what is an action, what are the the reference we are talking about. And could be machine translation as well, where we understand the structure that improve the translation accuracy. So what basically concept independency parsing as a in a comprehensive way, we can talk about heads and dependence. So each word in a sentence except the root depends on another word, which we call as head, right? So a dependency is a pair. What, let me define dependency in a clear way. So dependency is a pair between uh, a head and dependent, right? So let's say we have example, the cat chased a mouse, right? So this is the sentence, and let's try to find the dependencies here. So first word, let's say chased. This is the root word, right? This is the root word because this is the head of the sentence, right? Head. Next is cat. Cat is basically the subject or something that is being referred, and it depends on chased, right? Next is mouse. What mouse is? Basically, it's an object, which again depends on chased, right? Next, we have the word the. It's a modifier of cat, and we have again uh, which is modifier of mouse, right? Next, if we want to represent this particular sentence, we can write it as chased, or can I put a bit way like this? Similar. If you want to mention cat, chased, mouse, right? So this is how dependency parsing creates a tree structure. Yeah, this covers basic what dependency parsing is. And you can explore analytical libraries. There is a Stanford parser as well, and dependency parsing. We'll be giving the references for this stuff in the Discord server. If you haven't joined the Discord server yet, please join. Please also like to subscribe to this channel. And yeah, moving on to the next topic, that is co-reference resolution. I think we are already 28 minutes in this video. So let's try to cover next topic, and we are also coming with sequence models where we'll be covering RNN, LSTM, GRU stuff on the upcoming videos. So yeah, stay tuned. Let's catch up in next video. Yeah, thanks for watching.